Hey guys, we're going to talk about population parameters today, and it's really a statistical term. And we're going to go through some of the different parameters such as mean, standard deviation, and interquartile range. And those are things that you have seen before in Algebra 1. So we're going to look at some examples. For exercise 1, we have 18 students in an advanced calculus class, and we have their quiz grades. So I'm going to go ahead right now and pull up my calculator. I'm going to go to Stat and then Enter. And I'm going to pause the video right here, and when I come back, I'm going to have those 18 numbers in. So as you can see now, I have all those numbers in. You'll notice it says L119. That would be the 19th number. But I have 18 numbers in the list. And you want to make sure that number that's in the list matches the number in the question. So they want us to find the mean, the median, the quartiles for this data set, and then they want us to construct a box in Whisker Plot, which is something from algebra. So I'm going to go ahead, and what you got to do is you got to figure out the analysis by going to Calculate and then hitting Enter on one variable stat. The list is L1, and then you hit Calculate. Okay. So first off, mean is X bar. So we got X bar equals, and let's round these to the nearest tenth. So we got 83.7. So that's the average score based on the numbers that were there. Our standard deviation, median, excuse me, thinking of a different example. If you go down by pressing the down button, the median is 84.5. And the values that we need, I'm going to write all of them down, the minimum, the first quartile, the median, the third quartile, and the max. We need all 5 of those. Sometimes they call them the 5-number summary. So we got 56, 75, 84.5, 93, and 100. And this says do a simple box and whisker plot, or box plot. So what you want to do with a box plot is you want to create a scale. It's got to be universal. And you want it to encompass from the lowest number to the highest. So 56, I'm not really going to feel comfortable starting at 56. I'm going to start at 50. And then I'm going to put lines in for every 10. And I'm just going to try to space them out as evenly as I can. So for 56, you put dots above. So 56 would be about right here. 75 would be in the middle. 84.5 would be pretty close to the middle of 80 and 90. 93 is closer to 90 than 100, and then the max is 100. Now for the box plot, the 3 become the box in the middle, the quartiles and the median, and then lines get drawn to the minimum and the max. So the idea here is that as far as data goes, each of these sections has 25% of the numbers in it. So now moving on to B, the interquartile range. To find that interquartile range, you have to do the third quartile minus the first quartile. So in this case, this would be 93 minus 75, which would end up being 18. And they're saying, in theory, what percent of the numbers should lie between that? Well, in this case, that's from here to here, which is 2 quarters, which in this case would be 50%. Or in this case, the middle 50%. So they want to know if that's true for this data set. Well, let's see, because if we take from 75 here to 93 here, we should have, in this case, 50% of the numbers. And we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like we got a little more than 50% in this case. Now the population standard deviation is the one that's labeled S of X. And looks like they want us to round that to the nearest tenth. So in this case, S of X would be 12.0. Because up here it says 12.04. So the interpretation of the standard deviation, it means that for every 1 standard deviation, you should have a certain percentage numbers from that mean to that value. So the higher this value is, the more spread out the data is. So the data is spread out. So a small number would mean all the numbers in our data would be close together, and the larger the number, the more spread out they are. So you can kind of see that the lowest number is 56 to 100. So if you do a standard deviation of 12, after about 2 or 3 standard deviations, you should be able to encompass all the numbers, at least 99% of them. Now, in the case of part D, and I'm going to go ahead and kind of erase some of this. I'm going to erase the box plot as well. So we knew the mean was 83.7. So you're trying to find the percentages around that standard deviation. Well, it's 83.7. Now, we have to do plus and minus that 12.0. So we got to do a plus value and a minus value. And in the case of the numbers above, we'll pull those back up in a second. But if we add 12.0 to that, you're going to end up with 95.7. And if you subtract 12.0 from that, you're going to end up with 71.7. So the interval for this would be all the numbers between 71.7 and 95.7. So going back up to the list, anything between 72 and 96 or 95 would work. So in this case, we have from 72 to 95, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 numbers of the 18. So if I want to find the percentage of that, I would divide 13 by 18. And then you can multiply by 100 to get the percent. If you were to do 2 standard deviations, that's going to encompass pretty much almost everyone. So if I move back down to D, 2 standard deviations would be doing 24 away in each direction. So you're doubling that. So we have 83.7 plus or minus 24.0. And in the case of this, it would be 59.7 through 107.7. And if you go back up to the list, that's pretty much everyone except for one person. There was one that was a 56. So that'd be 17 out of 18. And again, you can divide that and multiply by 100 to get the percentage. So let's move on to the next example on the other side. And this one, the data is a little different because they have a frequency. So I'm going to go ahead and show you how to type in this data by pressing the stat button and enter. So I'm going to go ahead and start inputting the data. Now you can clear all the data out by hitting clear and enter. And then when I get back, you'll see that I have all the numbers in. So I have all the numbers inputted, and you'll see that I use L1 and L2 because there's 2 lists of numbers. Now for the frequency, what this means is that there are actually, so if I circle this 21, there are 21 32,000s. So 21 people have 32. So the calculator is going to interpret this as 21 32,000 is not just a 1. So to do that correctly in the calculator, you want to press stat, calc, go back to one variable stats, and then you'll see the part that says frequency list. So you want to put that as L2. So to do that, you hit the second button and the number 2, and then L2 will pop up. So then you go to calculate, and now we got some values for mean and standard deviation. So in the case of A, our mean is 42,060, and then the standard deviation, we'll use the sample for the population. The sample would be, S of x is going to be 16,736. And we'll leave that because we're talking about the values in the table are also in thousands as well. So I'm going to leave that as that. Now I'm going to move on to part 2, the median of this data. So the median ends up being the same as the first quarter, So the median is 32,000. And they're asking why is it so much lower? Well, if you go back to what I was talking about here, most of the data is on the low end. And we have this one number here, which we would call an outlier, where we have one person making that much money, but most of the data falls in this area. Most of the numbers are between 32 and 45,000. So that's kind of why our data in this case is different for the mean and the median. And in the case of Part C, does more or less than 50% of the data fall within one standard deviation? Well, let's take that mean, and we're going to subtract the 16,736. (0.60) plus 16,736. So we got 58,796. And then same thing, but let's subtract it. 25,324. So I end up between 25,324 and 58,796. So in this case, we have that many students, or sorry, employees. So we got 42 employees out of 50. So in this case, this is going to mean actually 84%, 0.84, which is 84%. So as far as 50% of the data, we actually have more than 50% of the data. We have 84% of the data between those values. Now, we can use that a lot of times to help us make predictions. And a lot of times when you're talking about mean or standard deviation, kind of like exercise 3 and 4, you're going to be adding and subtracting, trying to find a decimal. Sometimes maybe a proportion can be used as well. So for exercise 3, it says a questionnaire went home to the juniors, considering the ability to bring and use a mobile device. The census was of the 742 juniors, 564 of them said they had a web-enabled mobile device. So in this case, the population proportion would be that amount, 564, divided by 742. And our answer for that, we could get 564 divided by 742. We end up with 76%, so 0.76, which would convert to 76%. Now, if we're given a decimal, like with exercise 4, the percentage or the proportion of eggs that get cracked is 0.023. If we have 2,500 dozen eggs packaged, what should we expect to be the number of eggs cracked per day? Now, the trick with this one is they're trying to trick you with the 2,500 dozen. You actually have to multiply 2,500 times 12. And then you want to figure out 0.023, which is 2.3% of that number. So we have to multiply that by our 2,500 dozen. So it's 30,000 eggs. And if we multiply that by the 0.023, that gives us the answer of 690. So we have 690 eggs out of the 30,000 we would expect to have a crack in them. So if you need to, go review what I did earlier with typing in stat and getting the values in, especially when you have tables that might have a frequency as well. And also go back through and make sure you wrote down the symbols that represent the standard deviation, the population standard deviation, the mean, and the values for the box and whisker plot.